So we are going to solve practice problem 7.13 from Sadiku book. So the question is the switch S1 in the figure 7.54, this is the figure, is closed at t is equal to 0. So this switch will be closed at t is equal to 0. And switch S2 is closed at t is equal to 2 seconds. So this switch will be closed later when t is equal to 2 seconds. And we are asked to find IT. IT is the current that passed through this inductor here. IT for all t. So we will have three cases. Let's list all the cases. So the first one is when the switch is all open, which is when t is less than 0. And then the second case is when S1 is closed, so that is when t is greater than or equal to 0. And then the third one is when the S2 is closed, so it is when t is greater than or equal to 2. Okay, so we will check the cases one by one. And let's see the first case. Okay, now let's do the first case. Which is when t is less than 0. Okay, so let's see what condition that we have here. Okay, when t is less than 0, switch S1 is open, so all the circuit in the right hand side will be gone, and so we will only have this 6 ampere current source and this 15 ohm resistance. Okay, let's redraw the circuit. So this is the case. So we have a circuit here, 6 ampere and 15 ohm. This is 15 ohm resistance. So all the current will go through that 15 ohm resistance. Because this switch is open, there are no currents that goes there, so this I here will be 0. So when t is less than 0, we have IT is equal to 0 when t is less than 0. Okay, now we need to calculate I when t is equal to 0. So because the current in inductor cannot change instantaneously, so we can calculate I0 from this IT. So we'll have I0 is equal to 0. So we will have two important value here, and let's save this here. Okay, and let's clear the whiteboard after that. Okay, now let's see the second case, which is when t is greater than or equal to 0. Okay, let's see that. So when t is greater than or equal to 0, and our condition is S1 is closed. So S1 is closed. So we replace S1 with short circuit, and then S2 is open. Okay, S2 is open, and we need to charge this inductor with current. So let's see. Let's redraw the circuit with this condition. So now we have the circuit here. We replace S1 by short circuit and we replace S2 by open circuit. So we have this circuit here, and now we need to calculate I here, and I want to use KVL. Why we need to use KVL? Because inductor is easier to find the voltage in inductor than its current. So we need to use KVL. So let's make two loops here. And this loops, because this is current source, this loop will be 6 ampere. The current that passed through this is 6 ampere. And this loop here has the value of I here. Because I is here, so the value will be the same. And so we need to do KVL at loop I. KVL at loop I. Remember that KVL said that the sum of voltage in a loop will equal to 0. And one thing to note here, that the voltage across an inductor is V is equal to L di dt. Okay, so now let's start from this 15 ohm resistance. So I will have 15 multiplied by I, but here the current 6 ampere pass through the other direction. So I will have minus 6 here. And then we move on to this 10 ohm resistance, and we need to multiply it by I. And then this 20 ohm resistance, again we multiply it by I. And then this 5 Henry inductance. So we will have plus, the inductance is 5, and we need to multiply it by di dt. And all of this will equal to 0 because they form a loop. Okay, so now let's do a simple algebra to simplify this equation. Okay, we now have this, so I will have 15i minus 15 multiplied by 6 is 90, and this one will be 10 plus 20, which is 30i, and then plus 5 di dt. That will equal to 0. And then 15 plus 30 is 45. So we'll have 45. And then that multiplied by I. And I want to move this 90 to the right hand side. So I just add this with 5 di dt. So we'll have 5 di dt. And that will equal to 90 because we move 90 to the right hand side. Okay, now let's divide both sides by 5. Okay, we can divide both sides by 5. So I will have 9i plus di dt is equal to 18, right? Okay, so now we have this differential equation, but we also have that initial condition. So we should able to solve this. Okay, let's erase the board and solve this differential equation. Okay, now we have this differential equation, and this is the initial condition. I want to solve this differential equation. How? I want to multiply both sides by e to the 90, right? 9 multiplied by t, not 90, right? So I will have 9 multiplied by e to the 90, and I multiply this by I, plus, and this one is also multiplied by e to the 90. So I will have di over dt, and on the right hand side we also multiplied by 18 e to the 90. Okay, now we need to check this carefully here. If we check this and we name this as v, this di over dt is the differentiation of this one. So this is v prime, right? And then if we name this here as u, this is the differentiation of this u, right? So I will have u prime. And remember that if we have a function multiplied and then differentiated, we will have u prime v plus u v prime. So this can be written as a derivative of a function multiplication. So let's do that. D over dt. So u is e to the 90, e to the 90, and then v is I. So I will have I here. So this is the left hand side, and the right hand side still be 18 e to the 90. Okay, now I can move this dt to the right hand side, so I will have dt here and this one only d, and we can integrate both sides. Let's integrate both sides. Okay, so this integration will be just this inside the bracket, so I will have e to the 90 multiplied by I, and this one will be 2 e to the 9t, right, plus some integration constant c1. So now I can divide both sides by e to the 9t, so I will have I is equal to 2 plus c1 over e to the 9t. Or I can rewrite this as negative exponent, so I will have c1 multiplied by e minus 9t. Okay, because this is a function of time, I can rewrite I here as this one, I over time. Okay, now we need to find out this integration constant. How? From the initial condition. So the initial condition is I0 is equal to 0. Okay, let's do that. So when I0 is 0, we plug this 0 to this function. So we can plug that 2 plus c1 e to the minus 9 multiplied by 0 is equal to 0. So e to the 0 will be 1. So I will have 2 plus c1 is equal to 0, or c1 is equal to minus 2. So we can wrap this up. So when this t is greater than or equal to 0, it will be this function 2 plus c1. 2 plus c1. c1 is minus 2, so I can rewrite it as minus 2 e to the minus 9t. Okay, this is for t is greater than or equal to 0. Okay, but we still have one important things to do here before we move on to this, the third case, which is the initial condition for the third case. So our whiteboard is full. We need to clean this up first. Okay, now we have this function, and I want to evaluate the initial condition when t is equal to 2. So I want to evaluate I2. And remember, because the inductor cannot change its current instantaneously, we can just calculate I2 from the left, which is calculated from this function. So I will have 2 minus 2 e to the minus 9 multiplied by 2, or that will be 2 minus 2 divided by e to the 18. So my calculator here shows that the result is 1.111 with 71, so 79. So we'll have 1 2 3 4 5 6 7, and the last one is 7. Okay, because this is too many decimal points, I just approximate this with 2, right? So here I will have I2 is approximately 2, so it's equal to 2 here. And we need to move on to the third case. Let's clean the board and we start calculating the third case. Okay, in the third case, which is when t is greater than or equal to 2 seconds. Okay, now let's analyze what condition we have here. So S1 is closed, the same as before. And then S2 is also closed. And remember that we have the initial condition I2 is equal to 2. So I need to some space here. Okay, now let's draw the circuit that satisfy this condition. Okay, now we have this circuit here. I replace S1 here with short circuit and S2 with also short circuit. And take a note here, when S2 is shorted, all the current will be going through that short circuit, not these 20 ohm resistance. So that 20 ohm resistance become open circuit. So I just remove that 20 ohm resistance here. So we will have this simplified circuit, and we can do circuit analysis in this circuit, and I want to do KVL here and there. Okay, because this is I, the loop here also have the current I, and we have current source here 6 ampere, and that will be the value of this loop, which is 6 ampere here. So I can do KVL at loop I. So KVL at loop I. Okay, so KVL at loop I, we can just analyze here, and remember that KVL is said that the sum of voltage in a loop will equal to 0. So we need to start from this 15 ohm resistance. So we'll have 15 multiplied by I minus 6. And then we move on to that 10 ohm resistance. So I will have 10 multiplied by I. And then in inductance, we will have 5 di dt. Remember that the voltage through inductor is L di dt. So I will have this equation here. Let's simplify this a bit. So I will have 15I minus 60 plus 10I plus 5 di dt, right? So that will equal to 0. And I can move this 90 to the right hand side. So I will have 25I plus 5 di dt. That will equal to 90. Okay, let's divide both sides by 5. So I will have 5I plus di dt. That will equal to 18. Okay, and we have the initial condition of I2, right? I2 is 2. So I need to solve this first order differential equation with this initial condition. Okay, our whiteboard is full. Let's erase this and solve this equation. Okay, now I have this differential equation and this initial condition. So to solve this, I need to multiply both sides by e to the 5t. So I need to multiply this by e to the 5t. So we'll have 5 and I, and then plus e to the 5t. This is di dt. And this one is also 18 e to the 5t. Okay, and let's see on the right hand side, if we name this u. Okay, if we name this u, this is the derivative of u, right? So this is u prime. And if this is v, this is the derivative of v, right? So this is v prime. So remember that u prime v plus u v prime is a formula for derivative of function multiplication. So we can take out the derivative here. So we'll have d over dt of u, that is e to the 5t, and v, that is I. Okay, and on the right hand side we still have 18 e to the 5t, and we can move this dt to the right hand side. So I will have dt there, and this is d. So we can integrate both sides. And on the left hand side, I will have e to the 5ti. And on the right hand side, I will have 18 divided by 5, that is 3.6. E to the 5t. And we need to add it with some integration constant. Let's name that C2. Okay. Now we can divide both sides by e to the 5t. So I will have I is equal to 3.6 plus C2 over e to the 5t. Or I can rewrite this e to the 5t as negative exponent. So I will have C2 e to the negative 5t. Okay, so now we need to find out this integration constant here. How? This is the value when t is equal to 2, we have the value of this function is 2. So this I is a function of time, right? So I can rewrite that as this. So this is when we plug t is equal to 2 into this function. So we'll have 3.6 plus C2 e to the minus 5 multiplied by 2 is minus 10, and that will equal to 2. And this is not C1, this is C2, right? Okay, so I can move that to the right hand side. So I will have C2 e to the minus 10 is equal to, what is it? 2 minus 3.6 minus 1.6. So I will have C2 here is minus 1.6 divided by e to the minus 10, or I can rewrite that as 1.6 e to the 10. Okay, now we need to plug in this C2 into this function. Okay, our whiteboard is full. Let's erase this and continue. Okay, this is the function of it, and now I need to plug in this C2 into this function. So I will have it here is equal to 3.6 plus C2 is minus. Okay, we'll have minus 1.6 and then e to the 10, and then multiplied by e to the minus 5t. But we can join this function. This is e to the 10 and e to the minus 5t, so I can rewrite that as one exponential function. So 3.6 minus 1.6 e to the minus 5t plus 10, right? Plus 10. Okay, so I will have it is equal to 3.6 minus 1.6 e, and I can take out this minus 5 out, so I'll have minus 5 t minus 2. So this is when t is greater than or equal to 2 seconds. So I will have this one, it is 3.6 minus 1.6 e to the minus 5 t minus 2. So we answer, calculate it for all t. So this is the 3 cases. So when t is less than 0, it will be equal to 0. And this is when t is greater than or equal to 0, and when t is greater than or equal to 2. So this is the 3 cases. But we still need to find this I1 and I3. Okay, let's do that. So let's erase this and continue. So from here, we can calculate I1. I1 is this case when t is greater than or equal to 0. So I will have 2 minus 2 e to the minus 9 multiplied by 1. And so that will be 2 minus 2 divided by e to the minus to the 9. And let's give that to calculator. 2 minus 2 divided by e to the 9. Okay, so I will have 1.99975. ampere here. And for I3, we can use this function here. So we'll have I3 is equal to 3.6 minus 1.6 e to the minus 5, and our t is 3. So we'll have 3 minus 2. Okay, now I will have 3.6 minus 1.6 e to the, this is minus 5, right? Minus 5, or we can rewrite this as 3.6 minus 1.6 divided by e to the 5. And we need to use calculator in this one, so we'll have 3.6 minus 1.6 e to the 5. So I will have 3.5892 ampere. So this is the answer for I1 and I3. So hopefully I did not make any mistakes in the calculation. And thank you for watching. Do not forget to like the video and subscribe to my channel. Thank you. Bye bye.